A recommender is only impressive until a brand new user shows up. This is the setup you'll be able to run after this, which blends popularity and content to rank a new user against new and known items. I'm Professor Pi, teaching AI foundations with simple Python. Cold start is the hard part of recommenders. You have no clicks for a user and maybe new items with no history. Practically, teams need something useful right away. Success means landing a relevant top list within seconds, not waiting for weeks of data collection. In production, this often sits inside candidate generation, where fast, interpretable signals rule. At a high level, we combine three simple signals. Popularity gives safe defaults. Content tags capture stated interests. Small embeddings capture semantic closeness when tags fail. Mix them and you get a ranking that feels personal, even for new users. Strengths are speed and interpretability. Weaknesses are dependence on reasonable tags and representative popularity. We will build a small, clear pipeline you can run in Python. It returns a rent list for a cold user by combining popularity, content alignment, and embeddings, and it exposes one knob to tune the balance. That way, you can experiment quickly and see how changing the balance shifts recommendations. Now, we'll create a popularity baseline. This snippet ranks items by popularity for a brand new user with no data. The list items names your catalog, and the dictionary click stores a simple interaction count per item. The expression sorted with a lambda orders items by highest count first, then by name to break ties deterministically. The result pop rank is a stable popularity list, and slicing yields top 3 for immediate recommendations without needing any user history. This quick baseline is invaluable when you must show something relevant right away. The printed list confirms which items surface first, and the accompanying count explains the visible ranking strength. Next, we'll score items by content tags to match declared interests. This example scores each item from content tags using a lightweight user preference profile. The dictionary item tags maps items to interpretable tags, while prefs holds the user's interest weights. The function cscore adds up weights for an item's tags, giving higher scores to better matches. Sorting items by negative c-score and name produces a deterministic ranking that favors content alignment over raw popularity. This approach handles cold users who share stated interests but lack clicks. If you raise a tag's weight in prefs, items carrying that tag will climb. Reducing a weight lowers their rank. The printed best item and score show the strongest content match. Now we'll blend those signals into a hybrid score you can tune. This snippet blends popularity and content into a single hybrid score you can tune. The helper normalize rescales raw clicks in clicks to a 0-1 range, so popularity contributes comparably to content. The value Cmax captures the maximum content score, allowing C-score to be normalized per item. The function hscore then mixes both signals with alpha, controlling the trade-off. Larger alpha emphasizes popularity. Smaller alpha leans into content alignment. Items are sorted by this combined score for a decisive, stable ranking. Increasing alpha will typically promote already popular items. Decreasing it brings niche but relevant options forward. The printed winner and score reveal the current balance's top choice. Next, we lift content into tiny embeddings to compare users and items geometrically. This example uses cosine similarity over tiny embeddings to compare a user vector and item vectors. The dictionary item vec assigns each item a small numeric embedding, and uvec represents the cold user's intent in the same space. The function cos computes cosine similarity using math.hypot to normalize magnitudes, returning higher values for more aligned directions. Sorting items by negative cosine produces a deterministic ranking where near-parallel vectors win. This lifting via embeddings helps when content tags are sparse or mislabeled, as geometric proximity captures relatedness. Adjusting UVec shifts intent, changing which items align most closely. The printed best item and similarity show the closest embedding match. Finally, we'll re-rank by combining match, popularity, and novelty. This snippet produces a final re-rank that balances match quality, popularity, and novelty. The dictionary W sets interpretable weights for each signal, while novel rewards underexposed items by flipping the normalized popularity, poppin. The function F-score blends normalized popularity, normalized content score from C-score, and non-negative embedding similarity from COS with the novelty term. Sorting by this combined score yields a list that is relevant, familiar, and still willing to surface fresh options. Increasing the novelty weight lifts lesser-seen candidates. Reducing it steadies the list around proven items. The printed top 3 lets you verify the blend qualitatively and confirm the final ordering. In a real project, you would plug these pieces into a candidate generator and a light re-ranker. Popularity can come from a daily aggregation. Tags and small embeddings can be pre-computed. The re-rank step runs in milliseconds and gives product teams a transparent way to control freshness and relevance. Recap. This is a cold start ranking pipeline that mixes popularity, tag alignment, and tiny embeddings into a single ordered list. Use it when you need immediate, explainable recommendations for new users or new items. Caveat: it relies on decent tags or representative embeddings, so poor metadata weakens results. Next step: tune the alpha and novelty weights and measure how top positions change on holdout users. Or swap in an approximate nearest neighbor index for embeddings to scale up. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.